Okay, let's jump right into this explainer. Today, we're uncovering the universe's strict rulebook for how matter exists. When we look around, we see ice melting, water boiling, metal solidifying, but these aren't just random events, they are governed by incredibly precise mathematical blueprints. So, we're going to transition from abstract math to the actual real-world maps that dictate the state of literally every material in the cosmos. Here is our game plan to decode these cosmic rules. First, we'll define the chemical players. Second, calculate the degrees of freedom. Third, we'll actually derive the phase rule. Fourth, we'll map out water's phases. And finally, look at a complex system using solid sulfur. All right, Section 1, defining the chemical players. Before we do any math, we really need to know exactly who is interacting in our chemical systems. Our first major player is the phase. Simply put, a phase is basically any uniform state of matter in our system. It's a homogeneous part of a heterogeneous system, and it's separated from other parts by a clear, distinct boundary line. Think about a glass of ice water. The solid ice is one phase, and the liquid water is a completely separate second phase, because there's a distinct physical boundary between them. It could also be a pure gas, a solid alloy, or a totally mixed-up binary liquid. Next up, the component. And right here is a crucial distinction. A component isn't just any ingredient you toss into a beaker. It's strictly defined as the bare minimum, the absolute least number of independent chemical constituents needed to express the composition of all phases present in your system. It's the most efficient way to mathematically describe every single phase we just talked about. This abstract concept actually turns into a bit of a puzzle. Take a system of water, ice, and steam. You've got three distinct phases, right? But there's only one constituent, and exactly one component, H2O. But check out a complex system like ferric chloride and water. That system might exist in 8 different phases and have 6 unique chemical constituents floating around. But mathematically, it only has 2 core components. Why? Because every single one of those 8 phases can be perfectly described just by combining the formulas for ferric chloride and water. So you might be wondering, do component and constituent actually mean the same thing? The answer is a hard no. A constituent is any chemical individual that can be separated and exist outside the system. But the component is that absolute bare minimum requirement. So, while all components are constituents, not all constituents are components. You really have to strip the system down to its most efficient chemical description. Moving on to Section 2, calculating degrees of freedom. Let's figure out how much freedom our players have to change without entirely breaking the system. Now, degrees of freedom sounds kind of philosophical, doesn't it? But I promise, in thermodynamics, it's a very strict practical measurement. Think of it as the number of levers you can safely pull on your system. It's the minimum number of independent variables, like cranking up the heat or changing the pressure, that you can vary without accidentally destroying an existing phase or creating a brand new one. If your system has a degree of freedom of 1, it means you can change just one condition, say the temperature, and the physical state of your system stays completely stable. All right, Section 3, deriving the phase rule. It is time for the master equation. Let's see how this all comes together. We're going to build this master rule just like following a recipe. To find our independent degrees of freedom, which we call F, we take all possible variables and subtract the dependent ones. First, we grab our total variables, 2 state variables, pressure and temperature, plus our compositional variables. Then we find the dependent variables locked in by chemical equilibrium. Finally, we just subtract the dependent from the total to find our ultimate freedom. When you perfectly balance those independent and dependent variables, all that complex algebra beautifully collapses into this. F equals C minus P plus 2. Degrees of freedom equals components minus phases plus 2. It is incredibly simple, yet it completely dictates the physical limits of materials. Let's move to Section 4, mapping water's phases. We're going to pull this out of the theoretical realm and read the blueprint for something we interact with every single day. Take a look at a pressure-temperature diagram for a one-component system like water. With pressure on the y-axis and temperature on the x-axis, this map shows us exactly the conditions where water is solid ice, liquid, or a vapor. The boundaries between these regions are your melting, vaporization, and sublimation curves. Now let's apply our phase rule here. Water is one component, so C equals 1. In the wide-open regions, pure solid, pure liquid, or pure gas, we only have one phase. So 1 minus 1 plus 2 equals 2 degrees of freedom. This is a bivariant system. You can change both pressure and temperature independently, and it stays in that phase. But on the boundary lines where two phases coexist, like ice melting into water, P is 2. So F equals 1. It's univariant. Change the temperature, and nature forces you to change the pressure to match. And right at the center, the triple point. Solid, liquid, and gas all exist together. 3 phases. 1 minus 3 plus 2 equals exactly 0. 0 freedom. Nature has completely locked the pressure and temperature to one exact point. Section 5. Complex systems. We've seen water, but what happens when we add more solid phases to the mix? Let's check out sulfur. Things get pretty wild when you look at sulfur. It's a fascinating element because it can exist as two entirely different solid crystal structures, rhombic and monoclinic. Because it has these multiple solid identities, the map fractures into something far more intricate, complete with hidden metastable lines. Comparing the two, the differences are absolutely striking. Water features just a single solid phase and one simple triple point. Sulfur, because of its two distinct solid phases, creates this incredible web of 3 different stable triple points. You've got a point where solid rhombic, solid monoclinic, and vapor coexist. Another for solid monoclinic, liquid, and vapor. And a third where solid rhombic, solid monoclinic, and liquid all coexist perfectly at equilibrium. At every single one of those 3 points, our phase rule dictates that there are exactly 0 degrees of freedom. At the end of the day, understanding this rule gives you the power to read the true blueprints of the physical world. F equals C minus P plus 2 is not just a formula on a chalkboard. It's the strict boundary condition that materials scientists and engineers use every day to predict exactly how alloys will form, how chemicals will react under immense pressure, and how materials will behave in extreme conditions, like manufacturing or even in outer space. Which leaves us with a pretty fascinating thought to take away from this explainer. If an equation as elegantly simple as F equals C minus P plus 2 is strictly dictating the existence of the ice in your freezer and the sulfur deep within the earth, what other simple mathematical equations are silently, invisibly running the rest of the cosmos? Thanks for learning with me today.